So we were doing the inverse Laplace of this term and instead of splitting it up into the complex, conjugate, imaginary, real parts, and then dealing with all that algebra and the partial fraction expansion, we kept this together. And we matched it up with the Laplace tables. That look like this. And so we said alpha is 6, and omega n is the square root of 25 by matching these up. And then we can look at twice zeta, omega n is 6. And we found out that this was 3/5. Did we get that far last time? Did we do that? Get the damping ratio? I don't know. Well, we're doing it now. And then we have to fix it up, so we need the omega n squared, so we need a 25 here. So we just multiply and divide by 25. And then this is what we look up in the tables. And then we just need to multiply by 1 over 25 when it's all said and done. So the formula is this one down here, omega n squared s plus alpha. And here's what it turns into. Giant mess, but really it's just numbers. So we're going to plug in alpha here, zeta here, omega n. Let me see if I can zoom in a little bit here. There we go. And we have to calculate theta. It comes from this formula here, but it's not that big a deal. We're just going to stick numbers in for all of the values there. So we're going to end up with one over 25 times 5, the square root of 6 squared minus 2 times 6 times 3/5. So there's our zeta times 5 plus 25 over 1 minus 3/5 squared. So that's omega n. This is zeta, or yeah, the damping ratio. And then we end up with sine of 5 and then we crunch to the formula for theta. And while it looks like a lot of work, you got to admit that's faster than going through the partial fraction expansion and all that. Yeah. Oh, that's because I'm still sharing the screen. Thanks. So this is what we've been doing. So theta turns out to be 53.13 degrees. This turns out to be 4, which is the same frequency we got before. And this turns out to be 3. So that's e to the minus 3t. That's what we got before when we were doing this. Those are the roots that we got. And so our answer then ends up being, let me write that up top here. I'll tell you what, back. So I'm jumping over here rather than switching to the other board. So that's the first part, that's the 1 over S term, and then here's the part we've been working on. And so that's what you get. The damping is in e to the minus 3t, and then the frequency here is in radians per second. So that's typically the best way to handle terms where you end up with imaginary parts in the roots. Rather than splitting it up into the two parts, you leave it together, and then you look up the appropriate term in the tables like that. So we did one mass connected with springs and dampers. What if we have more than one mass? So we end up with two differential equations. Turns out it's no big deal. You just have two equations to solve for two unknowns instead of one. So I'm going to show you a quick example of how you deal with that, because for an airplane, we will have three equations and three unknowns. Like if we're talking a longitudinal flight, we have forward velocity, vertical velocity or alpha, and then pitch. So we got three equations and three unknowns. So let's not jump into that right away. And you should have talked through some of this when you did differential equations. Is that correct? You did more than one differential equation at a time, way back when. So we're going to do another mass spring damper system, but it's going to look like this. We're going to make it simpler. We're not going to put any dampers. We're just going to put springs and masses. All right, so we have two masses, so we have two free body diagrams, we get two equations. As we go through this, I'll show you how you do it one equation at a time, but then at the end, I'll show you how you can stick both equations into a standard form called state space form. And once you get to that point, it's not very hard to jump to three equations, or four, or five, or 100, or 1,000. It's the same exact form and the same exact format. All right, so free body diagram here. The force is on. Spring pulls back, force pulls forward. This spring pulls forward. And the pulling of this spring is going to depend upon the difference between this and this position. Right? If they both slide over the same amount, the spring doesn't stretch. But if x2 is bigger than x1, then that's when you get the stretching. So this has to be the difference between those two displacements. And then this mass has the force forward and that same force backward. Like that. So the equation, Newton's law here, sum of the forces. Got to make sure we put x1 here because it's the acceleration of this thing. So then the next step is to solve two equations into unknowns, differential equations. So we either use standard differential equation techniques where we plug in e to the st, or we Laplace both equations and go from there. So I'll show you both methods because they both end up with the exact same thing again. All right, so the differential equation method, we're going to plug in, we're going to assume obviously they have to be different, right? X1 is not necessarily x2. So we have to put an A here and a B here. You might say, well, use different S's, right? There may be different S's. That'll still look like an S. Right? Why not e to the st and then e to the wt? Kind of makes sense. It'd be something you'd want to try. But if we plug in for x1 and we have e to the st, but x2 has e to the wt, you can't cancel across. Remember, that's a key step in differential equations is you cancel all the e's out going across. So we have to see if this will work. Somebody have a question? No. The screen froze for the Zoomers. I forgot to thank you for watching the chat. Okay, so back over here now. So we plug in. We get the first equation, m1, and then you have a double derivative of e to the st. And there's no derivatives. And we're doing the homogeneous solution here, because that's the first step in the differential equation method, is to find that. And so you can see, because the e to the st is the same whether we have a or b in front of it, we can cancel out, so that gives us hope. Then we do the second equation. Get an s squared because you got a double derivative. And again, because we have the same form for both solutions, we can cancel out. That doesn't mean it's going to work. Again, most differential equation methods is you try something, and if it works, you go, oh, great, it worked. If it didn't work, you try something else. So now we're going to solve for A and B, because that's what we need. A and B are the differences between x1 and x2. Two equations, two unknowns, so you could just like solve and substitute and all that, but the more general technique, if we had 3 equations or 5 equations or 10,000, we'd want to put it into a matrix, right? So let's do that. So there's all the stuff that multiplies A up here. And then the stuff that multiplies B, K2. The stuff that multiplies B is oh, sorry, I need the A stuff there, don't I? So it's just minus K2. And now the B stuff over here. Homogeneous solution, so we got zeros here. So what's the answer? Yeah. That looks bad. Now that's dependent upon whether we can invert that matrix, right? So let's write that. So if the determinant of this thing is not 0, that means we can invert it. That means that we get a trivial answer and we just wasted our time. But the math guys have said, well, what about the other case? What if the determinant is 0? Then maybe we can get an A and B that works. And in fact, this is the solution we're looking for, is we set the determinant of that thing equal to 0. So the determinant is this times this minus this times this, and if it's 0, then we don't get the trivial solution. And if this bugs you, it should, because we've been trained all along that if we end up with a determinant of 0, or we can't solve the equation, there is no solution. But in this case, this actually gives us the S's that we want. And in fact, this is the characteristic polynomial. Just like we got when we were solving the other set, the mass by itself. So we have S's in here, so we solve this polynomial for S. And we'll put numbers in here that's going to make it clear what's actually going on. But in my personal opinion, that's always been kind of weird. But the Laplace method, again, cookbook, we'll just crunch, 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 and you'll see we get the same thing. How are we doing on time? Okay. Are you guys caught up here? Now I realize that we've been doing differential equations, and you're going, I'm an AE and I took flight dynamics. Why are we doing math? Well, it's because this is the math methods we use to analyze the airplane. So we're having to review it. So we're doing a little bit of math review here for a couple weeks, and then we'll use it. So there are our differential equations. And when we Laplace this, we're going to use 0 initial conditions. That we don't have to, but it just makes it easier when we talk about this. So understand that the method works perfectly well for non-zero initial conditions. It just would clutter it up with extra terms, and I don't want to get those clutters in there so that we can see exactly what's going on. All right, so let's Laplace this thing. We've got the Laplace of a second derivative. So I'm going to do that one first, and then I'm going to move the other side. So we get m1 s squared, because it's a double derivative. All right, once you got that down pat, you go, yeah, how many derivatives? That tells me how many s's we get. And then terms shoved over to the other side. Yeah, got k2 and a k1 times x1. And there's no derivative there, so we just get capital X. And then the last thing, we got a k2 times x2. Again, we're shoving these over the other side, so flip the sign. And then we can leave the forcing function in on this one because Laplace doesn't say, well, you have to do homogeneous in particular, you just do it. So this becomes f1 of s. So whenever we figure out what our forcing function is, impulse, step, whatever, we stick it in. And then the second equation, again, full derivative gives me an s squared. Shove this term over to the other side. So I get a k2 minus minus plus, but shove over, so I get a k2x1. And then I got the x2 term, which is k2 x2 of s, and that should be a plus, right? And notice that I'm kind of careful as to what order I write this in, because we're going to put it into a matrix, and if you write it with all the ones first and the twos second, then it's a lot easier to go into a matrix. Because now we're going to solve two equations for the two unknowns, the Laplace domain, and it's algebra from here on. Yeah. Yeah, absolutely. Sorry. And so we'll stick those equations into a matrix, because it's easier to do that, especially if we had 5 equations and 5 unknowns. Again, don't forget that, don't get freaked out because this is a function of s and this is a function of s. It's still, you just do algebra to figure out what this is, just like we do algebra for the one equation by itself. So here's the matrix problem for this. Oh, I got mixed up. What did I do? Well, I lost my x2 here. That's bad. There's my x1 term, and then here's my x. All right. The reason I kept looking over here, why is that? For the zoomers, take a look at this matrix here. Sorry, this one here. And let's go back over here to the one that we had with the differential equation technique and this matrix here. It's exactly the same. Just like the characteristic polynomial we got with the differential equation technique for the single mass, you got the same characteristic polynomial. And so if we use Cramer's rule, to solve this thing, x1 of s is going to be the determinant of the numerator, right? We replace the first column with the right-hand side. That goes in the top, but what goes in the bottom? The determinant of that matrix. Same thing for x2. We replace the second column with the right-hand side, put that in the top, put that matrix determinant in the bottom. And why am I not writing out the numerator? It's because I really don't care, because look at what shows up in the denominator. The characteristic polynomial that we would use for the partial fraction expansion is those terms that end up in the denominators of the partial fraction expansion. Those are the roots or the eigenvalues of the problem, which are the same as what we got over there on the other board. So we get the same roots from the determinant equals 0, because that's how we find the roots, right? We're going to expand this by the roots of this polynomial. So we find the roots, same deal as over there, and we go through the partial fraction expansion. We get to the e to the s, the e to the alpha t stuff, and we get the exact same solution as we got over there. So let's stop here. We're going to put in some numbers next time. Because I like to see numbers, and then we can calculate the actual frequencies and everything of the response. Stay here for a minute. I have quizzes to give. And then I will go over how both of these quizzes were graded on Monday.